Okay guys, this is 4.2, which is on modeling with linear functions. So basically, it's a fancy way of saying we're going to do some word problems with linear functions. And so when you're looking through these and you're trying to decide how you set them up, remember everything is going to be a linear equation. So you really want to identify what your independent variable is. So what is changing? And that's going to be kind of like your x value. And then what's the dependent variable? So what is depending on the changing part? And that's going to be your y value, or stand for y, okay, when you're writing these equations. Always, if it has an initial value or something like that, that's always going to be like plus something, almost like a y equals mx plus b. It's going to be kind of your b portion. If you're doing things where it gives you like, okay, in 2004, this is the amount, and in 2009, this is the amount, you set those up like they're ordered pairs, and then you can do slope and put them in y-intercept or slope-intercept form and be able to solve them that way. When they want to know when two things are equal, set your two equations equal to each other. When they want to know when one is bigger than the other, that's an inequality. Set it up like an inequality. You're welcome to graph things if that's a better thing for you. Draw pictures, because I honestly think pictures are one of the best ways to be able to kind of picture what you're looking at here. But really there's not a lot of notes here other than let's just do some examples and then get you on your way. So our first example, it says a town's population has grown linearly. Say that 10 times fast. In 2004, the population was 6,200, and by 2009, the population had grown to 8,100. And assume that trend continues linearly. And so because it is growing linearly, that means it's a constant change. We can assume that the rate of change here is a consistent change. So we can write an equation and then be able to use that to predict the population and then be able to identify when the population will reach 15,000. So what we first need to decide here is if we're going to write an equation, we need to decide what's going to be our inputs and our outputs, or your x's and your y's, your domain, your range, however you want to say it. We need to decide that portion of it, okay? So in this case, your x values, or your inputs, are going to be the years. So t in years, okay? And you can actually do this two different ways. Okay, no, never mind. I don't know what I was saying. Okay, so X is your input, and that's T years. And we're going to say since 2004, because that's when we're starting this, like, linear change. Before that, we don't know if it was linear change. We don't know if it was a consistent change every year. But we do know that from 2004 onward, it's going to be the same consistent growth, which is totally unrealistic, but, who am I? So our y values, or the outputs, are going to be the population, okay? So after however many years after 2004, what is our population? That's the dependent part, okay? So in order to kind of write an equation so that we can go through and be able to predict what's going to happen in 2013 and decide when we're going to reach a population of 15,000, we need to be able to write an equation. And because this is a linear equation, we need a slope and we need a y-intercept, okay? So to calculate your slope, what I'm going to do is I'm going to write the information they gave me in an ordered pair. If we're saying that my input is my years, and this is where you can kind of go a little bit different. Since we're saying T is years since 2004, you could say that 2004 is 0, and then that 2009 is 5. Or you can just say, okay, what is the change in your inputs over what is the change in your outputs? And either one is going to yield the same slope. So, I mean, don't worry about that. Because that change is going to be the same. So, since we're saying that T is the year since 2004, then I'm going to write my ordered pair as if 2004 is my initial year, that's 0. And the population in that year was 6,200. But again, if you wanted to write this as 2004, comma, 6,200, you could do that as well. They're both going to yield the same slope, okay? In 2009, the population had grown to 8,100, so that is going to be 5 years later. And that population is 8,100. Okay, and again, if you want to do 2009, 8,100, whatever. Okay, when I did this, I did the years. I did not do them as 0 and 5. I did them as 2009 and 2004. And it's the same thing as what we're going to do here in the book. So, I mean, that's not a big deal either way. So, we need to find the slope of this line, okay? Because that's going to be what that constant change is. That's what a slope is. It's how much is it, like, what is that change in 1 year, okay? So I'm going to do my y's first, so 8,100 minus 6,200 over 5 minus 0. So on the top there, 8,100 minus 6,200, that's going to give me 1,900 over 5. And if you divide that out, you get 380 people per year. So in 1 year, the population in this town is rising by 380 people. Okay? So what we can do is we can use this information to be able to write an equation. So we get y equals, well, we just found out that my m value was 380 times x, or times t, if you want to use t, however you want to do it. I'm actually going to use t for time, just because, and then I'm going to actually use this, and I'm going to put a p over here. But, again, it doesn't really matter. So p equals 380t, and then your b is where you start. So my initial population is 6,200, so plus 6,200 there, okay? So then, our next question is, okay, let's predict the population in 2013. Well, 2013 is 9 years past 2004. So if I want to predict the population in 2013, I'm going to let t equal 9, and I'm going to plug it into that equation, okay? So I get p equals 380 times 9 plus 6,200. And that tells me that the population in 2013 is 9,620, okay? It's a word problem, so I'd like for you to be able to write your answer in a word problem, like in a sentence, so that you can identify what's happening here. So, if our trend continues, our model predicts a population of 9,620 in 2013. Okay? So then part B says, okay, now we want to identify the year in which the population will reach 15,000. Okay? Well, if P needs to be 15,000, all we're going to do is substitute that in for P and solve for T, because we want to know how many years is it going to take to get there. Well, T is the number of years, okay? So, I'm going to do 15,000 equals 380T plus 6,200. You go through and solve that, you get 8,800 equals 380T. So then T is 23.158. Remember, we're talking about years here, so you can't have, you can have 0.158 years, but that doesn't make any sense. You'd want to say that either in days or in months or something like that. And since we don't really care, we're not going to be like super particular about it. We're just going to say the population will reach 15,000 in a little more than 23 years from 2004. Or you could say like in the year of 2017 or 2027, which would be 23 years from 2004. Okay? So that's also an acceptable way. You could say the population will reach 15,000 in a little more, or in the year of 2027. Sometime in the year of 2027. Okay? Okay. So the next one we're going to do says Anna and Emmanuel start at the same intersection. Anna walks east 4 miles per hour, while Emmanuel walks south at 3 miles per hour. They're communicating with a two-way radio that has a range of 2 miles. How long after they start walking will they fall out of radio contact? Okay, so I'm going to draw a little picture here. Okay, here's the intersection where they both start. Here's Anna. She's driving, or she's walking at 4 miles per hour. Okay. And here's Emmanuel. And he's going 3 miles per hour. And at some point, the distance between them can't get bigger than 2 miles. Okay? Or we want to know when it does get to 2 miles, because that's when they're going to fall out of communication. Okay? So, based off of what we got here, okay, if we know, and we're talking about, we want to know how long is it going to take. Okay, so how long means time here. Okay, so time in hours, or time, however you want to do it. Time in hours is probably the easiest, since they're walking per hour. Okay. So that means my input here is t, and that's going to be in hours, because they're walking 4 miles per hour or 3 miles per hour. And then our output, or our dependent part, is the distance between them. Okay? Now, they have 2 different distances. Okay? Anna, she has her own distance based off of her time. And Emmanuel has his own distance based off of his time. Okay? So we're going to have 2 equations, or 2 things here, okay? So Anna, she's going 4 miles per hour. So that's 4t. Her equation is 4t. And she starts at 0, so plus 0, I guess. And Emmanuel is going 3 miles per hour. So 3 times t. Okay? And if you notice in this picture we drew, it creates a right triangle. Okay? And we want to find the distance between them. We want to know when that distance is going to equal 2 miles. Okay? And if this is a right triangle, this would be your hypotenuse. Okay? So what we can do is we can take Anna's distance squared plus Emmanuel's distance squared. And that's going to be equal to the overall distance squared. You with me? I don't know why I said, are you with me? Because none of you can answer. So if I substitute in those values, I get 4t squared plus 3t squared equals, still the distance of t squared. Distribute that in, you get 16t squared plus 9t squared equals the distance squared. To get rid of this distance on this side, squared, I'm going to square root both sides. So in here, 16t squared plus 9t squared, that's 25t squared is going to be the distance between the two of them. When you take the square root of that, you're going to get plus or minus 5t. But distance can't be negative, so we're just going to write the positive one. Okay, so that means that this distance here is 5 miles per hour, basically. times the number of times, okay, or for the time. And we want to know when that's going to equal 2, okay? Because we can't be more than 2 miles apart, okay? So if the distance is like 5t, we're going to set that equal to 2 and solve for t. So t is 2/5. That time being 2/5, that doesn't make any sense. So if you take that and you convert it into hours, it's 0.4 hours. And you can leave it like that, or you can convert that to minutes, which would be 24 minutes. So it's going to take them 24 minutes to be apart from each other. Or well, be 2 miles apart from each other. Alright, I think this is the last one. No, we got 2 more. Blast. It says there's a straight road leading from the town of Lawrence to Kansas City. Change these towns. Which is 30 miles east and 10 miles north. Partway down this road, it junctions with a second road perpendicular to the first, leading to Spring Hill. Spring Hill is located 20 miles directly east of Lawrence. How far is the road from Lawrence? So let's draw a little picture. So here's Lawrence. And Lawrence is 30 miles east and 10 miles north. So over here, let's pretend Lawrence is here at 0, 0. Okay, let's say there's a little graph here. Okay, if I've gone 30 miles east and 10 miles north, then this point is located at 30, 10. Okay, and this is KC. All right, there's a straight load that connects them. Why am I graphing this? Well, because I'm doing linear equations, so it makes kind of some sense. So about partway down this road, we're going to have another road, and it's going to be perpendicular. Sorry, drew me. Okay? And this road is going to lead to Spring Hill. And our directions say that Spring Hill is directly 20 miles east of Lawrence. Well, if Lawrence is at 0, 0, that means that Spring Hill is at 20, 0. Because it's 20 miles away here. Okay, and this one was 30. Okay. I want to know how far is the road from this junction to Lawrence. So what is that little distance there? Okay. Well, if you remember back to geometry, if I know 2 coordinates in a coordinate plane, I can find the distance between 2 points by doing the square root of x2 minus x1 squared plus y2 minus y1 squared. That's supposed to be squared. So if I know LK is at 0, 0, if I could only find this point right here, then I could use the distance formula. Okay? So, that doesn't really help much. Except for, I know that it intersects, this point here is the intersection of the 2 lines. And if you remember back to Algebra 1, a point where the lines intersect is where their 2 equations are equal. Okay? So if I can write an equation for the line from Lawrence to Kansas City, and an equation of the line between the junction and Spring Hill, then I can set those 2 equations together, and then that will give me the ordered pair of the intersection, if that makes any sense. So what we're first going to do is we're going to find the distance between, or we're going to write an equation for the first line, which is from LK to KC. And in order to write that equation, I need a slope. So to find the slope, I'm going to take 10 minus 0, y minus y, over 30 minus 0. So that's going to be a third. Okay, so the equation is y equals 1/3 x plus, well, I need a b. Well, this starts at 0, 0, so that means b is 0. So the equation is y equals 1/3 x. Okay? Now I'm going to write the equation of the line from Spring Hill to the junction. Okay? That's going to be my second line, line 2. Okay? Well, here's the problem with doing line 2. I don't know the intersection point, so I don't have 2 points on that line. If I had that point, then I wouldn't have to do all the rest of this crap because I could just use the distance formula. But what I do know is that the line 2 is perpendicular to line 1. And line 1 had a slope of 1/3. So that means line 2 has a slope of -3. Perpendicular slopes. And I know that line 3 goes to the point 20, 0. So what I can do to write that equation is to do y minus y1, which would be 0, equals m, which is -3, times x minus 20. So I'm just using the point. This is basically what we did in the last lesson, where you have a line, an equation of a line, and you want to write the equation of a new line, but you only know 1 point on that line. Okay? So that gives me y equals -3x plus 60. Okay? So line 1's equation is 1/3 x. Line 2 equation is -3x plus 60. And from algebra 1, we remember that when those two lines intersect, that's going to give me this point right here. Okay? And when two lines intersect, that means their equations have to be equal. So the lines intersect when the equations are equal. So I'm going to set those equations equal to each other. So I get y equals, oh, snap. Y equals 1/3 x. Oh, I'm sorry, I don't need the y equals part because they both equal y equals. So 1/3 x equals -3x plus 60. I'm just going to set the two equations equal to each other. And then I'm going to solve. Okay, so if you want to solve, you're going to add your 3x over. Well, you have to find a common denominator. That's going to be 9/3 plus 1/3 makes 10/3 x. Equals 60. Multiply it by the reciprocal. So I got 10/3 because I added 1/3 and 3. If you use the calculator, you can do that. So 3 over 10. So I get x equals 18. I almost put 180, sorry. Okay, so x equals 18. So now what I can do is, well, now I know x equals 18. Okay, so going back to my picture, at this point right here, the x value is 18. I need to know the y value. Well, that point is on both lines. And any point that falls on the line, you can just plug that x value in and solve for y. So you can plug it into either equation and then solve for the y. I'm going to plug it into the easier one. So I'm going to go 1/3 times 18. And 1/3 of 18 is 6. So the y value is 6. Okay? So that tells me that the intersection point is at 18,6. Okay? So now I want to find the distance between 0, 0 and 18,6 because that's where the junction is. So find the distance between 0, 0 and 18,6. So you use your formula. D equals the square root of x minus x squared plus y minus y squared. Well, 18 squared, this whole thing ends up being, I'm not going to go through and do that because I was going to. And I don't have a calculator here, and I could do it, but I don't want to do 18 squared. So I'm just going to type it into Desmos. And when I typed it into Desmos, I got 18.97 miles. Okay. This is a word problem, so we're going to say the distance between the junction and Lawrence is about 18.97 miles. Okay. Last one. It says that Jamal is choosing between two truck rental companies. The first is Keep On Trucking, and it charges an upfront fee of $20 and then 59 cents per mile. So let's write the equation for Keep On Trucking. Since it's called Keep On Trucking, I'm going to call it K. And we're talking about, first of all, I'm sorry. We need to talk about inputs and outputs. I'm sorry, before I even write an equation. So inputs, that's like our X values. It's 20 cents per mile. So our input is going to be distance in miles. And our output is going to be the cost. Okay? In dollars. So how much does it cost at the end of this? Okay? Now we've got two companies, so we're going to have two different equations. So for Keep On Trucking, I'm going to call this K of D. So the cost for the distance using Keep On Trucking is an upfront fee of $20 plus 59 cents per mile. So 0.59 cents per mile. Move it your way. So I'm going to call this one M of D. They charge an upfront cost of $16, but then they charge 63 cents per mile after that. So 63 times the distance. We want to know, when will Keep On Trucking be a better choice for Jamal? So what we want to know is when K of D is going to be less than, the cost of that is going to be less than that of M of D. Okay? So what we're going to do is we're actually going to find out when they break even, because then every mile after that, K of D is going to be less than that. Does that make any sense? Okay. Or, moving is going to be bigger than that. So we're going to see when the break-even point is. When are the two equations going to be the same route? Okay? Because, and the reason we want to do this is because initially, here's the thing. Like, if we kind of, plot this in our head, K of D starts up here at 20. So initially, it costs more money. Okay? So it's moving along, okay? And M of D starts here at 16. And so it's cheaper until at this point right here. Okay? And after that mile, the darker blue line, which is K of D, so the Keep On Trucking, is going to be cheaper than the other one. So we want to know when that point is. Okay? What mile is that? How much distance is that? Because then any miles after that, K of D is going to be cheaper. Okay? So we're going to find out when they equal each other. So we're going to take 20 plus 0.59D. That's an A. What the heck? Equals 16 plus 0.63D. So then go ahead and move all your D's to one side, all your everything's to the other side. So that gives you 4 equals 0.04D. Divide by 0.04, or however you want to say that. So that's D equals 100. Okay, so this little mileage right here, D is our inputs, it's our X values. This is at 100 miles. At 100 miles, both plans are the same amount of money. Okay? The question asked us, when is Keep On Trucking going to be cheaper? Okay? So, Keep On Trucking will be the better deal. When more than 100 miles are driven. So when D is bigger than 100. And theoretically, you could just see, okay, well, if you wanted to do this a different way, instead of setting them equal to each other, you could have done the inequality and said, okay, when is this going to be, I'm sorry, no. Yeah. Yeah, I set that up wrong. I'm sorry. I'm so tired. You want to know when this side is going to be less than that. I don't know what I was doing there. I'm sorry. I knew it was wrong as soon as I drew it in, and then I was like trying to think it through. You want to know when Keep on Trucking is going to be less than the other moving company. So when you do that, I'm sorry. This is going to be 100. It's less than D. So we rewrite it as D is greater than 100. Sorry. Okay. So you can set it up as an inequality as well, or you can see when the break-even point is, and then you know it's any miles after that. That's going to be less. So either way is an acceptable way to set it up. Okay. Your homework for this section is page 317. You're going to do 9 through 44 all. I know that seems like a lot, but like you're setting up one equation for a lot of the, like, for like several of those problems. So like 13 through 18 is one equation and you're just manipulating it and putting in different information, so it's not that bad. And then 45, 47, 53, and 57. If you need any help, let me know. I think I uploaded the answer keys. I have not actually uploaded the answer keys for chapter 4, so I will get on that so you guys can check your answers as you go. And let me know if you guys need anything. Good luck.